Good afternoon. Last class we ended with a couple pictures where I was asking you guys to identify them. All of them were zoomed in pictures of things that I think most of them were things we are familiar with in everyday life, just at a scale we're not typically used to looking at them. I was going to show one, then I was looking online for similar pictures. I found a couple, and then we ended up doing 8 just because I thought they were all interesting. Thought it was interesting to see a staple at that scale. Kind of cool. But I didn't really explain how that came up in physics, what the heck we're doing. And here's what I just wanted you to do for a minute, including right now. And that is just think about some things that are typical things you experience kind of every day. But I want us to realize that at the, not necessarily microscopic, just pretty small scale, they have features that maybe we don't recognize, features that we're not quite familiar with. So there's a shaving razor in the top left. I think even after you clean a shaving razor, you think, oh, that's nice and shiny. It's actually probably pretty gross. Eyebrows, I think that's an eyebrow. They don't normally look that gross, but that's what they look like zoomed up. So that's going to become important today, our ability to think about things, some everyday things that we're familiar with, but just at a little bit smaller scale. And again, not super crazy scale, just zoomed in a little bit. Okay, and here's how that's going to come up. Today we're going to look at some forces. So we've been talking about Newton's laws, we've been talking about F equals ma, talking about forces have come up a lot. The force is, another word for force is a push or a pull. And the reason they're important is because in our universe, you cannot change the state of motion of an object without a force. If you ever see anything speed up, slow down, or take a left, that constitutes a change in velocity. Therefore, there must have been a push or a pull. So for us, if we're going to care about how the world works, we're usually going to care about changes of states of motion, and that always requires a force. And so when I see that something changes state of motion, I conclude there was a force. My next question is often, what was the force? What caused that? And today, it'll be a little bit of a squeeze, but I want to talk about, 7 of them? I would like to talk about at least several of those today. So first, weight, I don't think I'm going to spend much time on. I've already explained that weight is a special case of F equals ma. When I say weight, I can calculate it. It's worth writing down that nice relationship. The relationship is F equals ma. That's the relationship for weight. The reason you have a force, and remember I've also said I want to distinguish weight and gravity. So what is that force pulling you into your seat right now? It's not gravity, it's weight. That's just a little bit of semantics, but it's important for us to be accurate about how we talk about certain quantities in physics. So that force pulling you down into your seat right now, we're going to call that weight, and it's a product of two things. It's a product of two things. You have mass. All of us are made of stuff. That means we have mass. My mass can be calculated. The amount of stuff I have, add up all my protons, neutrons, electrons, I have a mass of around 70 kilograms. That mass, if I were in outer space, is still 70 kilograms. It's literally just an accounting of all my stuff. So put me out in outer space, I'm still 70 kilograms. Put me on the moon, I'm 70 kilograms. Go somewhere where I'm weightless, I still have 70 kilograms. I'm not massless, I'm weightless. So weight comes from the product of two things, your mass, and if you're sitting near a planet. It's usually the way we think of gravity. I mean, I guess it could be anything. It could be the person sitting next to you. But usually where we think of that lowercase g is the gravitational field created usually by planets. That's usually where we see significant sources of gravitational field. So if the whole universe was empty and it was just you and your friend floating out in space, your weight would be due to the gravitational field created by your friend. But it would be very, very, very small. Usually we're talking about things like planets. Okay, so that's weight. Weight is always, let's see, if things I would like to know about weight, it's a product of your mass and the gravitational field you're in, usually by a planet. And it's always pointing straight at the center of that planet. So for us, the curvature of the Earth is about, like that, because we're close enough to the Earth and it's big enough that toward the center of the Earth looks a lot like straight down. So here's the gravitational field for us. Now, if I were to hang two weights from two strings right here and right here, they'd look parallel. They wouldn't be parallel because they'd both be pointed to the center of the Earth. But the Earth's big enough that is almost never, ever, ever, ever relevant. So when I'm constructing my house, I don't have to care that if I were to build the easternmost wall of my house by hanging a string and the westernmost wall of my house by hanging a string, they would actually be, I'd be making a parallelogram because they would actually be pointing toward a common point. But unless my house is on a scale of like thousands of miles across, it's not going to be really relevant. It's pretty much going to be square. But it's nice to know, a nice little bit of trivia that anytime that weight, all our weights right now are all pointing to some common point about 4,000 miles below us right now. So all of our weight arrows are pointing like that. So if the Earth were to become if we all were to somehow fall through the Earth right now, we'd all meet at the middle. Okay. That's all I need to say about weight. Any questions? Cool. So you leave the Earth, you are weightless, you're not massless. That's an important distinction sometimes people forget. So when you're floating around like this, you still have stuff, you just aren't near a planet for it to matter. Okay. Normal force, that's a term that maybe hasn't come up in any of our previous experiences before. And normal, actually, so I think most of us think now the word normal means regular or average or something like that. Normal used to actually mean how physicists use it. Normal, back in the day when the word was first came around, Latin or something, it meant at a right angle or straight up and down. And I think you can imagine now that where that derivation came from. So normal means straight up and down or at right angles, and straight, it kind of means the same thing. Just like orthogonal for a physicist means right angles, and orthodoxy, means right or correct. So all the normal and correct and right angle and perpendicular, all those words kind of have similar roots. So that's just a way to help. The only reason I mention that is it helps me remember. So normal for a long time, for millennia, has meant right. And for a physicist, what that means is perpendicular to a surface. So when I'm describing certain forces in the universe, when I'm trying to think about how things work, I might describe a force as normal. And what a normal force is, it's the supportive force from any surface, and it's perpendicular to that surface. So there's a definition for the day, I guess. And I don't want to make this class about definitions, but it's nice to have common language. So if you put anything on a surface, if you just rest, right now I'm resting this clicker gizmo on this table. This table is supporting that clicker gizmo by what I would call the normal force, and normal forces are at right angles to the surface. So a normal force, by definition, means right angle. If I were to somehow if I had a surface with a weight on it, right now the net force on this weight is 0. I know it's 0 because it's not accelerating. Its state of motion is fixed. So I know that there's no net force on this. Here's where I probably am getting no net force. I'm probably getting weight down and normal up, and they're probably canceling out exactly. So that's why this weight is not accelerating down or up, because there's no net force on it. It's got its weight down. That weight would be 9.8 times something. So it's got its weight down, and then it's got a normal supportive force at an angle. Now, if I were to tilt this thing like this, the normal force is still perpendicular. So normal force is not always straight up. That's something to not get in the habit of thinking. Normal force is always perpendicular or at right angles to the surface. That's my definition. It's not my definition. That's the definition of normal. It's the right angle. So weight is always straight down, or at least pointed toward the center of the Earth. Normal is always perpendicular to a surface. Is there a question? Yep. Before it breaks. Right. Okay, that's a good question. The question is kind of like, what's my max normal force? So if I push on anything, we've already talked about this. If I push on anything, it's going to push back. So right now, I'm pushing on the floor is pushing back on me. Right now, my net force is 0. I've got a weight down of about 170, and the floor is pushing back conveniently at that exact same amount, equal and opposite. I'm not accelerating. The floor has only a certain amount of force it can supply before it fails to be able to, so it's made of stuff and stuff. And where that comes from, actually, we're probably not going to get too much into this class. It really comes from pressure more than force. And not to get too into it, but if I take my force, 170 pounds, and distribute it over two flat feet, the floor is pretty okay with that. If I were to take my 170 pounds and concentrate it on like a spike, I probably get that spike at least to make a dent in the floor. Still 170 pounds, but concentrated over a smaller area. And what happens at the molecular level, the tile atoms start going, that is just too much stress in one spot, and they eventually will leave each other. So I'll have 2 tile atoms going, all right, I can't handle this anymore, and they'll say sayonara. So if this were enough weight, the wood atoms here only are bonded, so strongly. So eventually, I could take this. It's got a number 14 on it. I'm going to go with 14 pounds. I could take this 14 pounds and distribute it over this nice area here, and this wood is okay with that. I could take that same 14 pounds and distribute it over a nail. I bet it would go into the wood. If I had a nail around here, we'd try it. But, yeah. So hopefully that answers your question. So technically, it does come down to how that force is distributed. So it'd be, if I were to take that, I could take the same 14 pounds, concentrate in a small enough area, eventually I could get wood atoms to do that. If I have a really, really, really sharp scalpel or an X-Acto knife or something, you may have run into this before, it doesn't take much force because it's so concentrated. So I could just take a tiny bit of force and go right through whatever I'm cutting through. Hopefully not my finger. Okay, good question. So just a couple definitions really to get us to where I wanted us to get to, and that is friction. And the reason I needed us to talk about normal is because I'm going to give us another equation for friction. Not to get too equation heavy. And again, I don't think I'll ever ask you to actually calculate, but I always want to write them down so you can see the relationships where they come from. Friction is also a force. I usually use lowercase f for friction. Friction comes from a normal force. The way you get friction is from a normal force. So friction is, well, let's maybe give a slight definition. Friction is a force between two surfaces, and it is always parallel to those two surfaces, to that interface. So friction is a force. These are all forces I'm talking about so far. Friction is a force that acts between two surfaces, and it comes from the interface between those two surfaces, and it depends on how squished together those two surfaces are. Another definition of normal force is a measure of how squished together two surfaces are. So right now, my feet and the floor are squished together with 170 pounds of force. So the amount of friction available to me, if I wanted to run out that door right now, I would need a force to push me out the door. I want to accelerate from here that way. I need a force. Here's where I'm going to get it. I'm going to get it from the friction between me and the floor. That's all I have available actually right now. If I had a rope, I could pull myself out the door. If I had a jetpack, I could shoot myself out the door. But most of the day as I'm walking around, I have none of those things. I only have friction. Even when I'm riding my bike, all I have is friction. When I'm riding my bike, the only thing accelerating me is the friction between my tires and the road. So if I want to accelerate a body, I need a force external to that body, and you need to be touching something. So either the ground, or I guess I could push myself off a table or something like that. But it's usually friction. So the amount of friction I have available to me has to do with my normal force and also something that we're going to call lowercase mu. If you've ever had to, your frat ever made you memorize the Greek alphabet, alpha, beta, gamma, delta, zeta, theta, mu. Mu, that's lowercase mu. So lowercase mu It's also the symbol used for micro. It's a fairly common Greek symbol. Lowercase mu is what we're going to call the friction coefficient. And here's how I like to think of the friction coefficient. Here's how I like to think of the friction coefficient. It's kind of a percentage. It's kind of a percentage of normal. So it's usually some number like 0.5, 0.2, 0.8, just some kind of percentage of your normal force. And so what that means is the amount of friction I have available for me to run out that door right now is some percentage of 170 pounds. So when I run out that door, I need something pushing me in that direction. And as I said, friction is always parallel to a surface. So the force I will get from the floor is parallel to the floor, which is great. That's the way I want to go, parallel to the floor. And I'm going to have some percentage of 170 pounds available. Now, I've got pretty slick tile floor with some dust and dirt on it, which makes it worse, and leather shoes. So that, all those things together, what the floor is made of, what my shoes are made of, and even how like dirty or dusty or wet it is, all those things together are going to combine to give me a mu of like 0.1. So I have about 17 pounds, 0.1 times my weight. I have about 17 pounds of force available to me. So I'm not going to be able to get out there very fast. So if there were something scary going on right over there, you would see me pulling like a Wile E. Coyote because these shoes are just, this floor is really dirty. So every time you see me walk over the chalkboard, I do like a little skid. I'm not trying to be funny or anything. It's so slick over here that it's really slippery. So yeah, maybe I need Roy running shoes to physics. So that's why I like to think of mu so several things combined that just give me a percentage. And so finally, we're kind of to the place where that's why I wanted us to be thinking about scale, because really what that mu has wrapped up in it is the interface between the two surfaces, between leather shoe and tile. And so in order to understand that interface, you can't just look at it and go, leather shoe, tile, because really what's happening, in order for me to get any force to shoot me out the door, I need those two surfaces to interlock or interface to some extent. Because really, at the micro level, the floor can't push me this way. I need to somehow interlock with the floor, and I need some sort of sideways force. Because right now, if the floor were perfectly flat and perfectly rigid, and so were my shoes, so glass floor, glass shoes, I couldn't get out the door as much as I wanted to. I would need a rope or to push off of something. So in order to get out the door, I need my shoes and whatever I'm standing on to interface somehow. So fortunately, this tile floor is sort of bumpy again, you don't have to get too microscopic, but you could probably even rub your hand across it, you'd realize it's not totally flat. And leather shoes are pretty rigid, but not entirely rigid. So when my shoe comes along, my shoe might look like this, but when I step onto that slightly bumpy surface, my shoe's actually going to go into those surfaces a little bit. And I can then get Newton's third law, equal and opposite forces pushing on each other. And so anytime you've ever put shoes on, maybe someone at the shoe company was thinking what you might be standing on. Well, they probably just think about what you look. Well, it depends on what the shoe's meant for. So some of them are just stylish, and I don't think anyone was thinking about I was going to be teaching physics in these shoes because they're not meant for that. Unless you want to demonstrate lack of friction, then they're great. But if you think about if I were to come into this classroom wearing soccer cleats, those soccer cleats were designed for maximum traction or friction. They were designed for maximum traction. So I might think, wow, this floor is terrible. Tomorrow I'm wearing soccer cleats because I know soccer cleats give me really good traction. I don't think that would work in here because those soccer cleats were designed to interface with a certain type of material or turf. And so soccer cleats on grass, soccer cleats on AstroTurf is great because it's this very soft surface and those spikes will drive in and I can get lots of side-to-side force. Like I said, even these shoes on this tile, I must be getting some side-to-side force or I wouldn't be able to walk around. But I need some sort of interface. So if I think about soccer cleats have these knobs that kind of dig into the turf. So they were designed specifically. So soccer cleats, great for grass field. If anyone's ever worn soccer cleats or like baseball cleats or football cleats on crappy like elementary school field that they've never watered and it's hard, you're wearing your soccer cleats and it's not helping a ton because the soccer cleats can't get into the dirt because it's like a hard, dry, caked surface. So you're always kind of worried about the interface. So if you run track, pretty much name a sport, someone at Nike is figuring out what you're going to be stepping on. So if you run track, my track shoes used to have little metal spikes, and that was meant for what I was going to be stepping on, a track, either a rubberized track or back in the day, I think we had like an asphalt track or some back in the day, people used to run on cinder tracks, but you had spikes that would go into that surface. So those spikes were probably not as great on grass, but pretty good for the track surface. Or if you run cross country, you have shorter spikes, so you kind of do both. I think volleyball shoes, think about trying to, or basketball shoes, I guess same thing. Like basketball or volleyball shoes are meant to be on a really slick basketball surface. And so with that slick basketball court, cleats aren't going to help. You need something really flexible that's going to find the little bumps. You know, most basketball courts are wood, so wood is naturally textured. So what you need is a nice flexible shoe that's probably going to have rubber and little ridges to make that rubber even more flexible, like little cuts through the rubber. So you might look at the bottom of a basketball shoe and go, how is that going to ever give you traction? It's like slick. Well, the reason is what you're trying to interface isn't like grass and roots and rocks. What you're trying to interface is the little bits of bump in a basketball floor. And the basketball floor, they're very little. So all you need is just something really squishy that's going to squish into those little bumps and give you traction. If you ever have a spare few seconds, like at the free throw line, you might see guys licking their fingers and cleaning off their shoes because I depend on that nice soft rubber and the interface between that and the wood to give me traction. Separate my shoe and the basketball floor with a little bit of dust or something, and all of a sudden I'm walking around on like ball bearings, and I'm going to slip. And so anytime you hear basketball players' shoes squeaking, that's a good sign. That means they're getting lots of good traction. Yeah, and you've seen that, right? They do that. They clean their, yeah, okay, I'm not making that up. Where else have I done that? Yeah, so, or like I used to be on a dodgeball team, with, right before the whistle goes, you're about to have to go race for the ball. You got to clean out your shoes off so you can get to the ball. Okay. And they probably make dodgeball shoes that have very specific surfaces just for whatever you're going to need to do in a dodgeball game. So I'm trying to think of other types of shoes, soccer cleats, track. Yeah, that's about it. So anyway, I think that probably covers it. So when you think about friction, you're concerned about what's going on at that interface. Same goes for bike tires and car tires and motorcycle tires. My car tires have treads. That's pretty good if you're trying to cover, my car tires probably are trying to cover a big range. So most people are going to drive in a range of different things. So if you're designing a shoe and you're going to design it for like just the BYU basketball court and that's it, you're going to need a lot of different shoes. So the shoe designer might try to have to like spread over a couple different types of surface. Same goes for car tires. Now, if I'm a race car driver, I might have a set of tires for one type of track and one type of condition, maybe one temperature. So I might be driving on a dry track and it's hot outside, and that's going to be a different set of tires than a cold track. Same track and it's cold outside, or maybe a different track that has different properties, or it's raining, or whatever. Let's talk a little bit about car tires, and I think we'll be able to move on. Yeah. So I'm pretty sure that race tracks are concrete or asphalt, something like that. So asphalt, you don't have to look very close to realize it's not that smooth. So here's my asphalt track. And here's my car tire. here's my car tire looking at it head on, so I'm looking from the back of my car. And so here's the car tire. And that car tire is made of rubber, so when the weight of the car pushes down into that asphalt, I'm going to get traction. And so if you ever looked at a race car tire, or even racing bike tires, a lot of times they look like that. They're totally smooth. So again, the idea that you need treads for traction, I think is a little bit misleading. You need treads for a couple reasons, not just to drive around on a racetrack. So if I was going to a racetrack and it was a nice day, it was dry outside, I would put my slicks on. Or if anyone ever here rides road bikes, if you ever look at a nice road bike tire, a lot of times they are perfectly smooth. When you look at a perfectly smooth tire, you think, how are you going to it's like on ice skates, you're going to wipe out. But actually you've got a lot of surface area there of a nice soft compound. You're going to get lots of good traction because that rubber is going to press into the road and you're going to get good traction. The only issue comes if there's something between you and that asphalt. So for example, say oil or rain or even dirt comes along and fills in that surface. So water will come in and do this. So if it rains, the water is going to fill in those gaps. Now when my tire comes and sits on top of that water, it's just going to hydroplane. It's going to skid. I'm not going to have much traction. So what I'm going to do is if I think I'm ever going to encounter water, and like I said, unless I'm at a racetrack and I know it's not going to rain, what I'm going to do is I'm going to build in little channels into my tire. So my tire actually has these channels that when I push down into the water can squirt up into those channels and I can still get in there. So if you have a nice flat surface and you're trying to get down into that concrete to get grip, it's not going to happen unless the water has somewhere to go. And so when I press down in there, I need to be able to get the water out of there. And so when you see a tire with treads, probably its main reason is to give water or other debris a place to go so you can get in there and get grip. And the other reason would be is if you're ever going to drive somewhere where the features you're trying to interface with are large. So my road bike tires are slick. My mountain bike tires have big knobs, and if I had a big Jeep or something that was going to go off-roading, those would probably also have big knobs. And the reason is, again, like I've been saying for the last 15 minutes, it's all about that interface. And so if what I'm interfacing with is roots and rocks and dirt, then I'm going to want big knobs that are kind of a similar feature size that I can crawl around on. But if all I'm going to interface with is asphalt, dirt, just flat, rubber is fine. Is that a question? Yep. That's a good question. The question was, how does traction control work? And that is, that's actually a very good question. So far what I've been talking about is the friction between two surfaces that are not moving relative to one another. So when I drive down the road, I don't want slippage. So what I need is when my tire rolls, I'll call this my tire, when my tire rolls down the street, where it's touching the road, there's actually not relative motion between, there's no slipping. There's no relative motion between where my tire's touching the road and the road itself. And so as my car moves relative to the road, I have a lot of stationary contact. So for an instant, where my car, does that make sense? So where my tire is touching is stationary relative to the road. If I get slipping, in other words, I get motion relative, so here's the road and my tire's doing this, my friction goes way down. And in fact, I was trying to decide if I was going to bring that up today, but yeah, that's a great question. So there's two frictions that physicists often are worried about, and there's static friction and kinetic friction. Static friction is always higher. So static friction is the friction, I'm really glad that came up. That's worth talking about. Static friction is the friction between two surfaces that are stationary relative to one another. Kinetic friction is the friction between two surfaces when they're slipping. And those are two different numbers. And kinetic friction is always lower. So as soon as my tires break loose, my friction coefficient goes way down. So my car can detect slipping. So my car can detect that's not right. We're going 5 miles an hour, but your wheel's going 60. So my car can cut power to the one that's slipping until it regains traction and try. So traction control is just a brain comparing the speeds of the car and the speeds of the wheels and slowing wheels down independently based on if it thinks it's slipping. Because you want to get back, especially if you're slipping, that's probably a bad thing, and the car wants to get you back to not slipping. And the way it'll do that is by lowering the speed. Anti-lock brakes actually work similarly. If I'm driving down the road and I just jam on the brakes, my wheels stop, all of a sudden I have sliding. And that has way less friction. It's going to take me a lot longer to stop. So my car goes, sorry, but I'm actually going to take the brakes off for you. Let the car's wheels start going again, and then apply brakes until they start slipping, and then let the car go, and then apply brakes until they start slipping. You can actually stop a lot quicker, because what the car is doing like 100 times a second is tightening the brakes till you start to lose traction, then letting them go, and then tightening them till you start to lose traction, letting them go. And so in both cases, traction control or anti-lock brakes, what you're doing is trying to get back to pure rolling, pure static friction. And so here's the demo that I didn't even think I was going to do, but let's try it. I hope this actually is visible to you. Let's try it. Let's go. No, I went over there. I don't know if I remember the number to get over there. I have 14 different. Hey, that's pretty good. I'll stop there. Okay. So right now, this is going to measure in newtons. That's the units of force. It's just going to measure in newtons how hard I have to pull to move this box. So I'm going to pull on this thing. It's going to measure 2, 3, 4, 5, 6. Okay. Hopefully you saw that. I'll try it again. It got up to like 10 or 11 static friction. So that thing's not moving. So what's the force opposing my pull? And I don't know if I mentioned this about friction. I don't think I did. Friction force, always parallel to the surface, mu normal, always opposes motion. That's part of the definition. Friction force always opposes motion. So I'm trying to pull this box to your left. So I'm trying to pull this box to the left. Friction is opposing me to the right. And this is measuring that force. It looks like I can get up to around 11 or so. That's the static friction. As soon as that box breaks free, you'll see the needle drop back. I think it dropped down to like 9 or so. So I can get it up to, so right now I'm using static friction, there. And see when it breaks free, the needle drops back. We see that? Okay, I'll do it one more time. So I can get up, let's try that again. So I'm going to get up to, I guess it was on a particularly sticky spot, but it always does drop back. So I can get up to 8, then it drops to 6. And if I keep it going a steady speed, if I'm going a steady speed, what's the net force on it? 0. So if I'm going a steady speed, I know the net force is 0. That means I know that my pull equals the friction. So in other words, I know this number is reading the friction. So here's a steady speed. Steady speed, 6.5 or so, 6.5. So if I'm going a steady speed, that means that the friction force is, the friction force is like 6 or 7 or so, yeah. But notice I can get up a lot higher before it starts moving. Okay, great question. So there's a demonstration of static versus kinetic friction. Oh, and then the other reason these weights are up here is to show that, well, I erased it. Friction goes up with normal force. So friction is a factor of mu, which is a measure of what's going on between these two, and mu's fixed here. It's always the two surfaces. So here mu is wood and whatever this is, particle board or something. So mu is fixed, but I can increase the normal force. So notice before I was getting up to like 11 or so before it started moving, I've just increased the normal force. And so now I can get up to 14 or so, then it drops down to like 12 or 11. And then I can drop more normal force in there. More normal force in there. I don't know. I might even max this thing out. Yeah. 22. There, 22. Okay. There we go. That's a demo of that. Okay. Any questions? Cool. Pardon? It didn't on that one, did it? It didn't drop back as much. As the normal force goes up, that difference is going to be less. So let's try that again. I think that was a good observation. I think that difference is going to be less. Oh wait. Oh no, actually, you know that is true. But actually, here's what's going on. I'm maxing out the scale. So the scale's at 20. That's as far as it goes. And so maybe here static is 25 and kinetic is 23. But in either case, I'm only reading 22. Okay. Let's see if I can do just this one. Yeah, I'm still maxed out at 22. Yeah, okay. Well, let's see if it might drop a little below. Yeah, okay. That one dropped a pretty good amount. Like 22 to 20. Okay. Yeah. Okay, we've got about 7 minutes left. Let's talk about spring force. We've already talked about here tension. Tension is the force due to rope. Okay. Drag. We've already talked about drag. That's just air resistance. We've already talked about the nice thing to know about drag. It depends on how fast you're going. Most of these other ones, that is not the case. So as we talked about, put my hand out the window at 0 miles an hour, put my hand out the window at 100 miles an hour, big difference. That's just drag force. Okay. Spring force, it comes up enough time in physics, and again, if I want to know how things work, enough things in this universe have a spring or a spring-like behavior in there somewhere. In other words, there's like something that's compressed and wants to be uncompressed, or something that's stretched and wants to be unstretched. There's enough things like that. It's nice to know about springy stuff. Here's how springy stuff works in 5 minutes. Sorry. Okay. I like graphs, and I think they help visualize things. Here's the graph of most materials in the world. Most materials in the world, if you pull on them, they stretch. That's what this is a graph of. If I pull or push on most materials, they will change distance. That's x. They'll stretch. And for most materials, at least for a little bit, that relationship between stretch and pull or push is linear, meaning it's a nice straight slope. So if I pull with 1 Newton of force and it stretches 1 meter, I'll pull 2 newtons, it'll stretch 2 meters. There's a nice linear relationship between pull and stretch, or push and stretch the other way, compress. Yeah. So most things I can do that. They're springy and I can stretch them. Now most materials will do that for a while, and then they will start to yield. And by yield, what I mean is when I'm pushing or pulling on anything, it doesn't matter if it's a piece of metal or a spring or a basketball or something, I'm going to get, when I push on this, I'm going to get deflection. It's going to change shape, it's going to change size, it's going to deform. If I push enough on that, kind of like we talked about with the limit to how much normal force I can apply, eventually I will pull on anything, whether it's a diamond or a spring, what doesn't matter what it is. I'll pull enough where the molecules start going, all right, that's enough, and they'll start rearranging. So if you've ever taken a paper clip, you can bend it a little bit, and it goes back to where it came from, and you bend it too much, it's stuck, it's deformed. Springs, if you've ever been playing with a slinky or something and stretch your slinky too much, that's what happens. The metal molecule said, all right, that's enough, and they are permanently deformed. That's what goes on. Can you see straight through this crazy thing? That's what's going on here. I've yielded my material, and when I let go, in other words, relax the force back to 0, it's not going to go back to 0 stretch. It's not going to go back to 0 displacement. This little x in here is my permanent deformation. I've permanently deformed the thing. So I can stretch, release, stretch, release. So when I stretch, release, and I don't exceed that force, I go up and down this little curve all day long. But if I pull too hard, I've deformed the thing, and now I've got permanent deformation. And then most materials will like even go like this, and then they will fail. Okay, that's most materials. In the last 3 minutes, here's a spring. I'm going to not go past the permanent deformation or yield strength of that spring. Jeez. I'm going to try to keep it in the linear part, and so what I'm going to do for the next 3 minutes is just add weight to this thing and hopefully get a nice linear stretch. In other words, a nice consistent stretch. So if I see that right now this is where the little red, oh, now I can push this one. Yeah. So I've got my nice, this is the stretch with just this much weight on it. Right now there's 50 grams on there. And if I add another 50 grams, it's going to stretch that much. This whole device is just to show you this next thing right here. This whole device exists, I think, for this reason. And that is to show you I'm going to add another 50 grams. And hopefully that stretch is the same amount. Hopefully those arrows are equally spaced. So that whole thing I just did right there was to show you that most materials have a springiness to them. And it doesn't have to be a spring to have springiness. And again, as we're trying to understand how things work, we're going to be talking about things that just deform. And that could be just about anything. Anything that deforms and goes back to its original position, like a basketball, that springiness is linear. If I push X amount, it stretches Y amount. I push 2X, it stretches 2Y. Okay, before you pack up, there's an equation for that. Okay, here's a bunch of equations. Please don't write them all down. I jokingly put the drag and the buoyancy equations up there. Definitely don't need to know them. If you're interested, they're true. They're not. I didn't just do this on the keyboard. That's real math. But what that shows you is that drag is proportional to the density of the fluid you're in, the velocity squared you're going, your drag coefficient, and your frontal area. But you don't need to care about that. The one I wanted you to see right now is spring force, and that's the equation up here. That's the equation of this line up here. And the one thing I wanted you to notice before we pack up, two things. One, that has a slope. That line has a slope. It's called K. That's the spring constant. Anything springy has a spring constant. That's just the slope of that line. And I want you to notice the negative sign in my equation. The negative sign means this, and this is totally mind-blowing. Springs oppose whatever you do to them. I pull on a spring, it pulls back. I push on a spring, it pushes back the other way. That's all that negative means. The negative sign just means pull on a spring, it pulls you back. Push on a spring, it pushes you back. Any questions? All right, please be here Monday. I think we're going to start some new stuff on Monday.